Okay, so we are talking about the 1D range search tree, 1D range search. So, this is the continuation of the last class. So, basically, so the idea is to start with a the root. So, we have the 1D range tree. So, we start with the root and then we go until we continue until we reach to a split node. So, split node means there is something interesting in the left part and there is something interesting in the right part. That means, there is some nodes which are in the range and there are some nodes in the right part also which are in the range. This is called split node. And then after the split node, we will keep on continuing in the left and right both sides. So, in the left part, so we again check. So, if there is nobody is interesting in the left part, we go to the right, and if we go to the left, then everybody will be interesting in the right part. So, we have to output this whole subtree. Okay, like this we continue. So, let us write the pseudocode for this. So, let us write the pseudocode for this. Okay, so this is basically 1D range search, 1D range query. So, the input is we have the tree, the range search tree, which this is the static data structure which we form by the given n points and a interval query. So, this x1 and x2 is the interval. Okay, so let us just write the pseudocode. So, we take W, the root of the tree in W. Then we will continue until we reach to a split node. Then while W is not a leaf and x2 is less than key of W or this or key of W is less than x1. Okay. So, either x is leaf, if it is leaf we stop, otherwise we check whether this is a split node or not. If it is a split, if it is not a split, this is by checking. So, so that means if, so this is the root, so this is the root, this is the key of W and we are looking for x1, x2. Now, we are looking for the points which are overlapping with x1, x2. Now, if x2 is less than key of W, that means our interval is completely in the left side, then we will go to the left part. Otherwise, if x1 is greater than key of W, then our interval will be on the right side. So, we have to search for this part, we have to search for this part either. So, if so that means it is not a split node. This is the checking that this is not a split node. So, that means there is nobody. So, either way we have to go. So, that is the idea. So, if this, then we have to go either left or right depending on this, whichever is the matching. So, this is the while this is do if x2 is less than equal to key of W, then we go to the left part, then W is left of W, otherwise 4, 5, otherwise else do if this, else W is right of W. Okay. So, this will continue until it reach to a leaf, we stop, otherwise it reach to a split node. So, after this for loop we reach to a split node. So, then after this for loop, so this is the observation. After this while loop, so either W is a leaf node, W is a leaf, or W is a split node. So, if it is split node, then we know, so this is our W. If it is split node, that means we know something is interesting here, something is interesting here. So, then we will do traverse both the way. So, but in the algorithm we will show the right only one part, then left part is the another part is the similar. So, let us just write this. So, this is 5, then we have a 6 over here. I am just deleting this. We got the split node say. Okay, so this will be 6. After that 5. Okay, so that means W is a split node. Now, if W is a leaf, then we just check the key of W with this, and if it is matching, if W is a leaf, then output the leaf output W if x1 is less than equal to key of W is less than equal to x2. Otherwise, if W is not a leaf, else that means W is a split node which is not a leaf, that means it has some child, left child or right child or both it may have. Okay, then so suppose we go to the then we take else V is basically left of W. So, this is the left traversal. Similarly, we have to do the right traversal also. So, we will not showing this. Okay. Then we continue while W is not a leaf. What we do if x1 is less than equal to key of V, sorry, V is not a leaf, if x1 is less than equal to key of V, then so if x1 is less than equal to key of V, that means this is our V. Okay. So, we are looking for x1, x2. Now, we know that something is interesting over here. Now, if x1 is less than equal to key of V, then we have to go to left part and we will output all the right part. Then that is the idea. If x1 is this, then output the subtree rooted at right of V, whole subtree rooted at right of V, and we go for left again, left of V, else we go for right of V until we reach to the leaf node or we reach to the situation where we have something interesting in left, then we have to output all the right subtree. So, that is the idea. So, finally, once we reach to the leaf, then we check. So, this is 9, 10, 11, 12, 13, 14, 15 maybe. So, finally, so this means we reach to a leaf, then we check, we output V if x1 is less than equal to key of V is less than equal to x2. Okay. So, this is the left traversal. Similarly, we have to traverse in the right part of the subtree. So, right traversal we need to do. Okay. So, now we have to analyze this. So, what is the time complexity of this? So, this is basically our tree is balanced. So, there are n nodes and it is basically log n height. So, basically what we are doing, we are traversing the tree. So, for each, and we are outputting the subtree. So, in any case we are just start from the root and we are going to the leaf. So, it is basically taking log n time. Time is log n for this traversal to go from the root to the leaf, and for each time. So, now after getting the output, after getting the tree, we need to, so basically we are getting these trees like this. So, after getting this tree, these are the answer, these leaves are the answer. Okay. So, to get these leaves, we need to spend order of k again. So, this is basically the time complexity for this query output. That means, we need to get this leaves. So, that is basically k plus log n is the time complexity for this. Now, what is the space? How many space? To store this, we need to have order of n is the space, and to form the tree, we need to have order of n log n. That is the space complexity, and this is the time complexity is this. Now, the question is, this is a very nice data structure. The question is, the advantage is we can extend this for 2 dimensional or higher dimensional. So, that is the idea. So, that is the 2D tree, 2D range tree. Okay. So, the question is how we can extend this for 2D. So, basically now we have seen the 1D range tree. Now, how we can extend this for 2D. So, what is the way? So, 2D range search means what we do? So, we have a 2 dimensional points. Okay. And 2D range search means we have a rectangle like this, we have a rectangular box, a rectangle. So, what we do? We first take a 1D range search. Okay. So, basically the idea is we store the points. So, we store the point in 1D range search tree. So, that is the primary tree. So, primary 1D range tree, this is the primary tree based on x axis value. Okay. Now, if we do that, then and if we give the interval query, then we will get the. So, on that we will just do this query. So, we start with the root. So, this is our 1D range tree based on the x value, x coordinate. So, we have this root, we start with the root, we go left, then we go right like this. So, until we reach to a say split node. Once we reach this the split node. So, once we reach to a split node, then again we continue. So, if we go right, then if we go left, then this all the these are relevant. Then again from here like this, like this, like this. So, similarly we will go here. So, like this, like this, like this. So, basically these are our output. So, these are our points whose x axis are which are in this strip, whose x axis are on the range x1 x2, but we want y axis to be on the range xy x2. So, these are the points whose x axis are matching. Now, what we do? We have a secondary range tree. So, we have a secondary tree structure and we will store it based on the y axis. Okay. So, the another secondary range tree we will store, and that will be based on the. So, secondary 1D range tree. This is also your pre-processing phase based on the y coordinate, y axis. So, if we do based on the y axis, so that means, so we have, so we have the points, we have n points, each point is having x coordinate, y coordinate. So, on the on the x coordinate we have this range tree and we got this subtrees, and on the y coordinate also we have the range tree. So, we have lots of data structure is going on. So, on the y coordinate also we make the range tree, and there, so we have for these points we have similar kind of structure is there for the y coordinate. So, these points will be just so So, these points will be like this, like this. Okay. So, these are based on the y coordinate. So, we have the similar same size tree, but these are based on the y coordinate. Okay. We have like this. So, this is the range, this is the part of the range tree in the y coordinate, because we so these their size is same, because this number is same. So, now what we do? Now, for each of these we do the range 1D range search query. So, we have a y1 y2, we have a y interval. So, we do the range search, we start with this root, we go here until we reach to a split node. So, this is the split node, then we continue. If we go right, then all these are relevant, like this we continue. So, these are the points where y axis is also matching. So, these are the points we are looking for. So, these are the points where y axis is also matching. So, that is the idea. So, basically what we are doing, we have two range. So, basically we are having two data structure, two range tree. One is based on primary range tree, one is based on the x axis we store in a tree, and then the second one is based on the y axis we store in a tree for all the points, because we do not know which points will come into this. So, lots of data structure is going on. So, then we first apply our 1D range search query on this x axis, we got some subtree, and we have similar. So, this is the similar data structure. We have the similar data structure with the same nodes here based on the y axis. Okay. And then in that tree we have to do the 1D range search based on the y coordinate, and that will give us basically the matching of the y coordinate also. So, that will give us the points which are in the rectangle. So, that is the idea. So, this can extend for further dimension. So, on this, if we have x, y, z axis, we have another ternary range tree, and there we have to search. So, this will match x axis, y axis, z axis. So, this is the idea. So, what is the time complexity for this? So, for this we are basically log n square, because this is the log n, and here again we need to go for log n square for each. Suppose there are log n tree, subtree. So, time is basically log n square. And so, after knowing the subtree, if we have to report all the elements, then it will be k plus log n square. If k is this is the output sensitive. If k is the number of points which are lying in that rectangle, then it will be k plus log n square. Okay. And pre-processing time is same. Pre-processing time is basically same as earlier, it is basically n log n, and the space is also. So, now if you want to generalize this for d dimensional, then query time will be taking 2 to the power this to the power d, because we have d many such dimension, and each dimension we have to search it. So, okay. So, we will just quickly look at another problem, geometric problem, and this has lot of application in the database system, because basically we are so this range search tree has lot of application. What is those? Because suppose we have a n dimensional d dimensional data, n data which is d dimensional. Okay. So, suppose student records, each student has many attributes. So, d dimensional, so say marks in or CGPA, age, like this. So, there are many dimensions, and the marks in algorithm, marks in some mechanics, something. So, now these are the dimensions. So, based on this we store it. Now, suppose we have a query like this, we just have a points like this x1, x2, then so suppose it is say 3D, then we have a range like this, okay, and we want to see how many points are belongs to this. So that means we want to fix that, okay. Microsoft came for the campusing. So Microsoft wants database of the all student, name of the all student whose CGPA lies between 7.9 to 9.9 and whose algorithm marks is basically lies between 90% to 100%. This is the 2-dimensional range search. So we have to get all the students whose matching with this range. So this is a rectangular search, 2D search. So there are lots of application of range search tree. Anyway, let us have a quick another problem which is called line segment intersection problem. So the problem is basically this is also static data structure. So we have some lines, we have few line segments. Say we have n line segments, and we need to find out any two segments are intersect or not. Okay. So does any pair intersect? That is the problem. So for example, if we have a line segment, say this is a line A to A, say, and say we have a line like this, okay, suppose this is A, B, C, D line, this is line segment, not line. Line has no starting point and ending point, but segment has starting point, this is E line. Okay. So suppose these are our input, there are n line segments. Now we want to know is any pair of this segment are intersect. So that is the idea. So what is the naive approach? So we can take any two segment and we can just check by coordinate wise whether they are intersecting or not. So that will take order of n square, because there are NC2 pairs. So we just take any two pairs and then we check. But we want to do is something better way, that is called sweep line algorithm. Sweep line algorithm. So basically what we are doing in sweep line algorithm, we are having a vertical line. So we just move this vertical line this way. So we have a vertical line. So we move this vertical line like this. Okay. Like this. So this should be continuous, but it cannot have a continuous. So this is the movement of vertical line. So we move until we end to the this. Now, so while moving, what we observe? So we observe the ordering of this intersect. So this is the intersect point of the line. This is the intersect. So here, so if it is starting from here, intersect. So we are interested in these intersecting points, and if we maintain a data structure, dynamic data structure with these intersecting points, and this we are putting in the order of the value of the y axis. So this is the value of the y axis ordering. So if you do that, so this is basically the ordering is basically like this. So this is basically A is finished. So this is CB, this is also CB, this is also CB, this is also CB. Now B is finished, this is only C, this is nobody is there. So this is basically DE, and this is also DE, this is also DE. This is basically So, sorry, this is D, this is E, say. This is basically ED. Okay. So, we maintain a dynamic set S for this storing these numbers, this y value. Now, so when this value will change, in the three conditions this value will change, either when a new line is entered, new value is entered, that means a line segment has joined. So, that way, and when a line is finished, then it will change. Otherwise, it will change when there is a intersection, because here it has changed. Here there is a change because B has finished. Okay. Here there is a change because C and B has joined. So, either this change will occur, either a new segment is joining or a segment is leaving, or they are crossing, they are intersecting. So, we have the interest here. So, how to check? Then whenever a change is occurring, we will see the neighboring node, we will see the neighboring lines and we will check whether they are intersecting or not. So, for this dynamic set, this set S, we need to maintain a data structure. So, what we can do? We can use the red black tree, which is balanced, and that will be done in order of n log n time. Anyway, this is the rough idea of this sweep dying algorithm. So, if you have interest, you can look at the textbook for the details of the pseudocode. Thank you.